Howdy guys, today we are doing problem 2.26 from the textbook. This question gives you this MIPS code right over here, and part 1 asks, assume register T1 is initialized to the value 10. What is the value in register S2, assuming S2 is initially 0? Alright, let's get that put in. So here we have the beginning. We start with 10 as our value for T1 and 0 for our value S2. Alright, the first instruction up is the set less than. So we're comparing 0 to T1, and if 0 is less than T1, T2 gets set to 0, or excuse me, set to 1. Otherwise, it's 0. And so here we have T1 equals 10, and 0 is clearly less than 10. So our T2 becomes 1. Our next instruction, BEQ, branch on equal. Our value T2 equals 1. So it does not equal T2, and our branch will not be taken. So we continue down. Next instruction, submediate, where we subtract our immediate value from our register and store it over here. So we have, this would be like an equivalent C statement, T1 equals T1 minus 1. So our T1 of 10 now becomes 9. Next instruction, add immediate. Pretty similar. S2 equals S2 plus 2. So our S2 was 0. Now it is 2. And we go J loop. We jump back up to our loop tag, and we are set right here. So I went ahead and put that into a table for us. This was our beginning values. These are our values after the first iteration through our loop. Okay, and for the second iteration, I'm not going to go through it in as much detail. It's pretty similar. We have 9 and 2 are our initial values. T1 is still greater than 0 because it's 9, so our T2 stays 1. Our T2 still as a 1 does not equal 0, so we continue on, do not branch. T1, subtract another 1 from T1, and that gives us 8. Our add immediate, we'll add a second 2 to get the value of 4, and jump back up to the loop tag, the very beginning of our instruction. So let's see, here we have our updated table. Similarly for the third one, and you're starting to begin to see a pattern here. You have 10, 9, 8, 7, and then 0, 2, 4, 6. So let's start to look at when would this not, when were we gonna break this loop condition. So for us to branch, our T2 has to be equal to 0. So we start looking up here at T2. So that's our SLT line, set less than line, which will be 0 when we have a 0. Even, I guess, equal to 0 would be the first time that our set less than would go to 0, or would set T2 to 0. So let's move on up. So we can predict these all the way up till our T1 will be 0 going into the next loop. So we have done 10 iterations of the loop. We now have 0 as our T1 value and 20 as our S2 value. And let's see how that goes through the program. Our SLT line, T2 is what we set. we're comparing 0 and T1. T1 is 0. They're both 0, and our T2 then is set to 0. Now we go to our branch statement BEQ, and we're comparing our T2, which is 0, to 0, and now they're finally equivalent, so we will branch to the done tag, which is right here. Alright, so that's going to be our value S2 will be 20 because we skip over all of this stuff and we no longer update S2 or T1. So, but once we hit done, our program is completed, or this portion of the program would be completed, and our values T1 equals 0 and S2 equals 20. So let's actually head over to the MIPS and check it out. Alright, we're over here in our Mars, which is a MIPS simulator. We have initialized our values T1 to 10 and S2 to 0. And then we have our program down here, just exactly the same as we had in our problem statement. So let's go ahead and take a look at what's going to happen as we run this. We can step through it. So we initialize our value 10 and 0. We come to our set less than statement, and our T2 is set to 1. Go through our branch, we do our sub immediate, our add immediate, jump back up, and we continue to do this loop, and you can see that it's operating just normally. So let's just skip to the end to verify that our value should be 20. Okay, here we are. This is our value of S2, and it's saying it is 14 in hexadecimal, which is equivalent to 20 in decimal. And our value of T1 is 0. So that verifies that we got the right answer over on paper. Alright, the second part of this problem we're going to be looking at, this is more of like an algebraic type problem for this exact same code. And it says for the loops written in the MIPS assembly, assume that the register T1 is initialized to a value in, unknown value in, and then they're asking how many MIPS instructions are executed. So I started over here with the case n equal to 0, and notice that when n is equal to 0, we just go through set less than. Our T2 will be set to 0 because these are equivalent, and then our branch statement is equivalent. T2 equals 0, which equals 0. So we do take the branch to done, and that is our instruction. So when you end up with your values S2 equal to 0, and I guess they're asking for how many MIPS instructions, and you only did 2, the set less than and the BEQ, so that is 2 instructions. Alright, now for our in values that are greater than 0, the program runs in loops until it reaches the beginning where T1 equals 0. And we remember that from part 1. Here, let me just go back and show you. So our in value here would be this 10, and we run 10 loops until we get T1 down to 0, and then we head into the final execution of the loop. So we have in loops of the program until this T1. Each of the full loops is 6 instructions, 1, 2, 3, 4, 5, you say, but sub immediate is not native. It's actually just going to be an add immediate and then a native sub instruction, as we saw with our in the MIPS. Here, let me actually show you that. As you can see here in the Mars simulator, here's the sub immediate instruction, and it's actually being replaced in runtime by an add immediate and a sub instruction. All right, so that's 6 instructions for every in, and then we have the 2 instructions on the final loop where t1 equals 0. So we have the instructions equals in times 6 plus 2, and that's for n greater than or equal to 0. And I'll just say that your in has to be greater than or equal to 0. If it's negative, I guess there's not really a way to do a negative number. I think all the ins should be unsigned. Alright, well, that about does it for this problem. Thanks for watching. Hope it was educational.